I hope you are familiar with elastic wave propagation. So we have a simple spring system here, but if you add some plasticity to it, weird things happen. In the example you have just seen, the elastic wave was part of this elastic transition between two cutoff peaks. This is a very similar method as used in Coulomb, Tresca, von Mises yield envelopes, but it's in 1D. So you have deformation or displacement or strain or any other displacement equivalent coordinate on the x-axis, and force or stress or shear stress, whatever resistance equivalent variable on the y-axis. And each spring has a stiffness, and as long as the spring load is within this range, it behaves elastic. As soon as it hits the peak, it becomes plastic. And as you have seen in an example, when this is hit in a dynamic simulation, the spring length is no longer limited. It goes towards infinity. And there are many different ways of nonlinear elasticity. You can have this stiffness in a curve, and as long as it's elasticity, you always go through the same zero value. So if it's a log normal curve, you will go in something like this. So maybe in extension, length is increasing and the reaction force remains constant. So you might get cut off in a way. And in a compression, stiffness rapidly increases and it becomes incompressible beyond some point. You can also have an exponential third order, fifth order stiffness, and that way you will have infinite reaction force at some deformation level in both directions. And here is an example of exponential stiffness. Small amplitude waves move slower than large amplitude waves because the propagation speed is proportional to ratio between mass and stiffness. And if you have exponential stiffness, as you could expect, at high deformations you have higher stiffness and a different propagation speed. Now, because you have limited stiffness in plastic models, unlike the exponential one, where the deformation is limited by rapid increase in stiffness, in plastic models we cannot run simulations on a simple spring system. We need some way of balancing the system. So the following simulations use this simple anchored soft springs with a elasto-plastic or plastic or nonlinear stiffness springs on top. So the wave is propagating above. That changes the dynamic a little bit, but the changes are not substantial as long as you stay in the elastic range. So here you can see the elastic propagation in the anchored system. The wave shape is not changing much after reflection, and there is not really much going on, as you would expect. However, the behavior of the wave changes quite significantly if you insert log normal stiffness, which means no resistance in extension at some point, and big resistance in compression. The waves become more triangular at the peaks, more sharp, and it's quite clearly visible, that change in stiffness. And there's also a change in wave propagation velocity depending on the phase which the springs are in. The springs in extension are transferring energy slower forward than waves in compression, so the compressive part is pushing. Now, the most interesting type of wave propagation for me is elasto-plastic multi-envelope, or something nearly pure plastic, like this case, where the load goes up following one stiffness curve and the unloading follows a different stiffness curve, and then reloading would follow another stiffness curve. So you basically have two stiffness curves governing the elastic, elastoplastic, or plastic behavior, you could say, pick one. And this type of system, just like this elastoplastic cutoff, it allows permanent deformations. You could end up unloading to zero and staying at some permanent deformation. Unlike with nonlinear elasticity, where unloading to zero always leads back to the same zero. So the waves can leave permanently deformed springs behind them as they propagate. Here is an example of such a Coulomb springs being overloaded, and the hysteresis dissipates most of the energy. And then, similar to the example given in the opening, if you insert a very small level of energy, small force envelopes, upon reflection the springs interact with each other and can actually cause crossing the threshold. And here is a little longer example of waves propagating and leaving behind permanent deformations, bouncing off from the left and leaving a deformed piece of springs there, and from the right as well. Such systems of springs, they have many interesting properties. They can actually reflect off of themselves, and as you can see here, the shape of the wave changes a lot, and depending on the phase of the spring, the energy is transmitted differently. And you have whip effects and all kind of features which are not actually part of any research I know of, and that's one of the reasons why I'm testing this concept and giving it in such a primitive, basic form. Here's an example of a simulation where the variables happen to produce an interesting phenomenon in which the spring loses stiffness and then disconnects, releasing the amplitude of the mass, and that causes a wave to propagate backwards. Right about here you can see the energy is redistributed within the plastic, and then there's a wave traveling backwards. So the waves interfere with themselves. And this is where things start to become very different from standard elasticity. The waves can actually collide with each other instead of merely superpositioning. You can see here two waves crashing, and they produce a break in the chain. And from that break, new waves are introduced into the system in both directions, with a very sharp breaking point there in the middle. Now, if you had been working with dynamics, FEM, elasticity, plasticity, you will notice that dynamic wave propagation in plastic medium is not a very common topic. In fact, I did not find many YouTube videos about it at all. And this kind of behavior is very computationally costly to model. That's one of the reasons, and normally it's done by discretizing this curve into many stress envelopes. And in my simulations, I started doing these because I found this alternative way of modeling using deformation envelopes, which actually generates the same result. By P.J. Yoder has been the biggest influence, and there's not much literature on the topic, and no one's really researching it, but I find it quite powerful because it can give you the same physical answer of reaction force using one equation less. And instead of having a series spring system, you actually have a parallel spring system, which is parallelizable very efficiently. You can run it on GPUs, but because you have sparse matrices, maybe you can harvest some extra power from parallel CPUs. Anyway, it's a very simple way of doing it, but it's unusual in a sense that we don't really have any plastic strains. There are no plastic deformations recorded. The plastic deformation is generated by an internal force, which elongates the spring length, and we just sum the forces correcting for the spring length. So if you make a initial load here, the elastic prediction is that one, and then there's a distance from the actual physical curve that your model models, and so this delta is added into the internal forces, forcing the spring to elongate, and then your applied force is still at a distance from the physical value, giving another delta, which is then added. So you have this stress relaxation approach, which is, it does exactly the same thing, but we don't convert the internal forces into plastic strains and then convert them back into internal forces later. We just remove this step from the equation. And it makes computation of dynamic elasto-plasticity or even pure plastic materials very computationally efficient. You avoid a lot of matrix inversions, which are computationally costly, and yeah, it just solves it much faster. And another benefit of these deformation strain envelope models is, besides being very computationally efficient, they allow you to model things from a different perspective. So in this example, you can see on the top left, there's these many envelopes yielding and relocating using kinematic hardening rules. In the middle, you can see volumetric response being modeled. And the volume is generated by combining the total effect of each envelope individually on the top right. And on the bottom, you can see the hysteresis. The thing I find truly amazing about this concept is how parallel computation compatible it really is. Because you can have yielding and volumetric change and the hysteresis and everything in branchless code without using if statements. So by simply having sigmoid functions or similar methods for computing it. So it's extremely compatible with parallel processing due to its branchless, fundamentally branchless conceptual structure. And yeah, it can model a lot of things which are not technically possible using conventional approaches. It gives a whole new branch of models to explore and try to analyze, implement. I am pretty surprised that nobody is really doing that, because it's a whole new field, a whole new branch of science. Yeah, and here are some examples of this, the hysteresis loops, the stiffness, which is relevant to these spring systems. You can have stiffness hysteresis loops of different inclination, different angle, depending on how you distribute the envelopes, what parameters you set into them. Yeah, so this is pretty much approaching the end of the video, and I would like to show one final example where you have colliding waves, and this is the picture you get when you show the full deformation, the internal forces and the external forces, so elastic and plastic deformations combined. And it can be a little hard to see how the energy propagates, if any energy is propagating at all through the system, because some of this can be just a local oscillation around the anchoring node. So to make things more understandable, it's pretty easy using this concept to isolate the energy carried by the elastic and by the plastic deformation mode. And if you plot those separately, you can actually see how much of the energy is stored in the spring elastically and how much was left in the plastic range. For example, if you take the F external and multiply it on the inverse matrix, you will get the elastic component. So if you plot only the deformation that is due to elastic deformation, you get something like this. And you can see that the wave got completely eaten up. The wave coming from the right got completely eaten up. And then there's a reflection of a small amplitude wave in a hysteresis loop. The small amplitude is the stiffest part, so you could expect that high stiffness at low amplitudes will produce higher velocity waves. And in the end, yep, we are ending up with just standing wave oscillating around the anchoring node. Similarly, you can plot only the plastic component, the F internal multiplied by inverse stiffness matrix, and then you can see how much energy is being dissipated. Each time this value changes, some energy is taken out of the system. And that can be interesting to analyze to get an understanding of how the energy dissipation is looking inside the system. So in conclusion, I think it would be very interesting if someone was interested in researching deformation envelope models, because they open up this fascinating potential of modeling dynamic wave propagation in nonlinear materials using very efficient computation. And this can be beyond geotechnics, where I work in earthquakes, skyscrapers, components. It can be cars crashing and wind turbines, and all kinds of things can be modeled with this very extremely efficiently, and a lot of new phenomena become visible and potentially resolved. And seeing how P.J. Yoder had published this unprecedented work of his and defended it in many public defenses and so forth, and it was left so unnoticed, it really makes me lose faith in publishing anything anywhere.